Okay, this says draw dipole moment diagrams, and then it gives you several molecules. What we're going to do is we're going to go through the process of figuring out whether each of these molecules is polar or not polar. And so there's a step-by-step process, which I'm going to outline here and do the example of CO, and then I'm going to move to a different page to do the other ones. If you want to squeeze them in, you'll have to draw smaller than I draw them. But the first thing you ask yourself when you're looking at a molecule and trying to decide if it's polar or not polar is you have to draw the Lewis structure. And there is no way around it. You cannot tell by looking. You have to have the Lewis structure because you have to know where the lone pairs are in that molecule in order to tell if it is polar or not polar. So carbon dioxide, just going to jot it down because we've done it before. Looks like that. Okay, then the next thing you need to do is know the EPG-MG, the electron pair geometry and the molecular geometry. The C has two domains on it, so it's linear, no lone pairs, linear, linear. Okay, linear, linear. Okay, next thing you do is ask yourself, are the bonds polar? So is this bond right here, is it even polar? Well, C to O is 2.5 to 3.5, so a difference of 1. So yes, the bonds are polar. Yes, the bonds are polar. If the bonds aren't polar, we would just move on. Like without polar bonds, it's difficult, if impossible, to make a polar molecule. So without polar bonds, we would just say no, at least at the level we're at right now. But this has polar bonds, so we need to continue to investigate further. The next thing we investigate is something called symmetry. And that's not something we've talked about yet. But symmetry is what exists whenever, imagine we had, this was a person. Imagine this was a person. Pick a person in the class, okay? Imagine this was Stephanie Gump, okay? And then two of her friends, equally strong friends, maybe like Kaylee and Megan, are pulling on Stephanie, pulling on her, and they're pulling equal amounts from here and from here. Stephanie doesn't end up moving, even though she may feel uncomfortable by the pulling, but she doesn't end up moving because neither one of them can win. So that's what we call symmetry. So yes, that is symmetrical. Yes, that is symmetrical. And symmetry destroys polarity. Symmetry destroys polarity. So is the molecule polar? No, it is not, because symmetry destroys polarity. Okay, then let's next do water. Now water, from just glancing at the structure, looks very similar to CO2. It's got a central atom with two other atoms, but if you draw the Lewis structure, you see that it is not at all similar. On this Lewis structure, you have 4 domains, and 2 of them are filled with lone pairs. So the 4 domains means that the EPG is tetrahedral, and the molecular geometry is bent. And that bentness is going to make a very big difference to us. The fact that this molecule is bent is a very important thing. Okay, so this is how that molecule appears. Okay, so imagine, so are the bonds polar? We check H to O. H is 2.1, O is 3.5, so the bonds are polar, yes. Now we check symmetry. Now imagine this is Stephanie again, and Megan and Kaylee are pulling on her exactly the same amount, but they stood here. What's going to happen? As they pull on her, Stephanie's going to move this way, right? They're yanking on her. She's coming with them, going this direction. So there is not symmetry. She gets moved. That means there's no symmetry. No symmetry? No symmetry to cancel out the polarity of the bonds means the molecule is polar. And in fact, water being polar has changed, is that fact, and it changes how life on the planet works. So is water polar? You should just answer yes, water is polar. You should just memorize that one, water is polar. But because it has no symmetry, that's how you get polarity. So before we move on to looking at other ones, I want to look at our chart here and talk about which ones could be symmetrical. Which ones could be symmetrical? Well, in linear, we just discussed how linear could be symmetrical. So I'm going to put a little purple dot on it. It could be symmetrical. It wouldn't be symmetrical if, let's say, instead of having this be like this, instead over here, you had this guy. Now that's not symmetrical because this guy and this guy are totally different. Even though they're quite opposite of each other, they're totally different. So that wouldn't count as symmetry. But if the two things opposite each other are the same, that molecule is symmetrical. Okay, next let's look at trigonal planar. Now imagine we have three people pulling equally on this guy in the center, pulling exactly equally. Well, they are exactly spread out. So again, the guy in the middle doesn't move. So trigonal planar could be symmetrical. Trigonal planar could be symmetrical. However, if you switch this guy out for this guy and now one of them's different, then you lose the symmetry. Okay, but trigonal planar could be symmetrical. Then, if we lose a bond pair and make it a lone pair, now it's bent. Bent is for sure asymmetrical. Bent is always asymmetrical. So this molecule could definitely be polar. If it had polar bonds, it would be a polar molecule. Okay, let's look at tetrahedral next. It may be hard to imagine it. You have to imagine that this person is like in a swimming pool, okay? And so they're floating at the top of the pool, and these three friends are spread out evenly, but a little bit below, and they're all pulling their friend down, right? But somebody is like hanging from the ceiling above and is pulling their friend back up, so again, they all cancel out because they've actually been spread out exactly from each other. So tetrahedral could be symmetrical. Tetrahedral could be symmetrical. But if I take one away and make this a lone pair, now the three buddies are all trying to drown their friend here, and there's no one helping him from the top. So that is asymmetrical. This one would be polar if the bonds are polar. Or if we take another one away, that's the bent of water we were just talking about. Also asymmetrical. The two friends are pulling this way and it would move. Okay, let's look at trigonal bipyramidal next. Picked up the wrong one. Okay, when it's like this is actually symmetrical because this guy and this guy cancel each other out but have no effect on these three guys, and then these three guys are like the trigonal planar and they're all pulling evenly. So trigonal bipyramidal can be symmetrical. Then you remove one and it's seesaw. This is no longer symmetrical. These two cancel, but these two are pulling down and no canceling to the top, so that is not symmetrical. Then you pull another one, you get T-shaped, also not symmetrical. These two cancel, but this one's on its own. But if you move another one and you get linear, now linear could be symmetrical. If those two atoms on either side are the same, then that would be symmetrical. So I marked that with a purple dot there. Now let's look at octahedral. Octahedral, it's kind of easy to see the symmetry. Each guy has somebody canceling him exactly on the other side. These two cancel each other, these two cancel each other, these two cancel each other. So that's symmetrical. Square pyramidal, we remove one. Not symmetrical anymore. This guy has lost his buddy, so no longer symmetrical. But then square planar, now these two have canceled each other. These guys still have their buddies, so square planar can be symmetrical. So any of the shapes that have the purple dot could have their polarity canceled by symmetry. The ones without the purple dot are going to be automatically polar if they have polar bonds because they are not symmetrical. So let's go ahead and try another molecule. Let's look at BF3. Okay, BF3 looks like that. So it has three domains, trigonal planar, no electron pairs, so it's trigonal planar. Are the bonds polar? Well, B to F we did up here. Yes, the bonds are polar. Is the molecule symmetrical? The molecule is symmetrical. Look, trigonal planar is in our possible symmetry one. So yes, the molecule is symmetrical. So is it polar? No. Okay. I ran out of room to do this sideways, so I'm going to do them below. Now what about COCl2? Okay, 3 domains, 1, 2, 3. So it's trigonal planar, trigonal planar. Are the bonds polar? Well, C to O is polar, and C to Cl is polar. So, yes, the bonds are polar. Yes, bonds are polar. Is this symmetrical? No, because these two, the chlorines, their electronegativity is 3. So they are weaker than this guy whose electronegativity is 3.5. So imagine this was like, I don't know, who do you think is the strongest in our class? Maybe Kyle. Okay, so this is like Kyle tugging, and this is Kaylee and Megan. And so Kyle is stronger, and he pulls harder. And so this is not symmetrical. The person stuck in the middle being tugged on is definitely going to move. So no symmetry. So yes, polar. Yes, polar molecule. Yes, polar molecule. Okay, now let's look at another thing that's got 3 bonds on it, NH3. NH3 is a little different than the other two because it has 4 domains instead of 3. So 4 domains means the EPG is tetrahedral, but the molecular geometry, trigonal pyramidal. So are the bonds polar? Yes, the bonds are polar. Is the shape symmetrical? No symmetry. Because remember that one's this one, trigonal pyramidal. There's not symmetry there. So is it polar? Yes, it's a polar molecule. Okay, and I'm not going to film page 26, but I am going to film a tutorial that's related to homework 8.4. So please try homework 8.4 before you watch the tutorial, because the tutorial is going to take us through our results to 8.4. So it'll show you all your answers, so it'd be in your best interest to try it first. It'll show you all the answers to 8.4, but then it's going to ask the question, are these molecules polar, as a way to keep practicing this. And then after that, you do homework 8.5, where you go through a bunch of different molecules and try and figure out if they're polar or non-polar. And feel free to contact me. I will still open up office hours to talk to you anytime before June 1 if you are struggling to understand it. Okay, take care, and I hope you have a very good summer, and I see you again soon at workshop.